Okay, so today we're going to talk about prime and composite numbers. So one way to determine the positive factors, or remember factors are also known as divisors, of whole numbers is to use a rectangular array. That is, you build an array, which must be a rectangle, out of however many units you have. So I made an example here for 12. You see we could have one row of 12. That would represent 1 times 12. And then I have 2 rows of 6. 2 times 6 is also 12. And 3 rows of 4. 3 times 4 is also 12. And there's no other way that we can put together a rectangle that would comprise of 12 units. I also made a quick example of 6. A prime number is a number that only has 2 factors. Those factors are 1 and itself, meaning there are no other numbers that divide into it. A number that's not prime is called a composite number, and composite numbers can be expressed as the product of 2 or more prime numbers put together. And here's an example I have for you: 18, which is equal to 2 times 9. 9 is not a prime number, so if we broke 9 down into 3 times 3, we would have 2 times 3 times 3. Also, we could have not seen 2 times 9. We could have seen it as 3 times 6. If we saw it as 3 times 6, that would also break down to the exact same prime factorization, would be 2 times 3 times 3. We write our prime factorization with powers as a product of multiple prime numbers raised to a power. That's how we write them. Okay. This is called the sieve of Eratosthenes, and I'm sure I said that wrong, but basically this is a tool to finding prime numbers that was discovered back in 200 BC, which is just crazy. And we're not going to find all these numbers, but I did think that it was worthy of me to talk to you about how it works. And also, you know, this is something that can be done at several different levels. The first thing you do is you triangle up the 1, because 1 is neither prime nor composite. 1 is a special number. And then you would go to 2, which is our first prime number, and we'd circle up the primes. And then what we would do at this point, once you come up to a prime, you then scratch out all of the multiples of that number. Now, you could do this as simply in an early class by saying that we need to count by 2. So we would say 1, 2 cross this, 1, 2 cross that, 1, 2 cross that, or we could say everything that's a multiple of 2. 10 is divided by 2 because it's even. 12, 14, 16, 18. I'm not going to do very many, but I'll do just a few so we can see the pattern here. So I'll go here to 30. And then you would go to the next prime number, and the next prime number available would be the next number that's not marked out, and that would be 3. And then we would go through and we would mark out all of the multiples of 3. And if you were not good with multiples of 3, it would be every third remaining square. So here's 1, 2, 3, 1, 2, 3, 1, 2, 3, or if we were a little bit more advanced and we knew what the multiples of 3 are, we could cross those out. Then that brings us to the next prime. And again, just the same thing. Once we've gotten to that next number, we know that it is a prime number, and then at that point we start taking out multiples of that prime, and it looks like the only multiple that's left here is 25. Now, that's kind of interesting, that what is the square of 5? It's 25. That was the first number that was left in the list after we crossed out the other numbers. And I'm going to kind of point out the fact that when we did 3, that first number that was open to be crossed out was 9, which happens to be 3 square. So I would expect that when we did the number 7, the next number that would not actually have been crossed out from all the previous primes would be 49. Anyhow, this is a very cool, interesting little tool here that is pretty portable. So remember, we circle the primes and we remove all the multiples of that prime, and then what we're going to be left with is a list of all the primes. All right. So here are a few tools that we use in prime factorization. So the first and probably the most used one is something that's called the scaffold. And what we do here is we start off with our 945. And it's kind of like that upside down long division mark, and we're going to put a little box around that. And we're going to choose a number that goes into 945. Well, we know for sure 5 goes into 945 from the divisibility rules. And when we put 9 in there, we're left with 189. And then we just keep on going down. Let's see, 189, 9 and 9 is 18, so that's divisible by 3. So let's divide that guy by 3, and when we divide it by 3, we get 63. Looks like that too is divisible by 3. 3 goes into 63 21 times. That is also divisible by 3. I like to, once I get on a roll with a number, I'm going to ride that number until I can no longer ride that number, and then the final number that we're left with here is 7. So we can see here that the prime factors And if I'm just going to list them here, it looks like I've got a 5 times a 3 times a 3 times a 3 times a 7. Now, we want to write that in a little bit more organized and more sophisticated way. We want to put it in ascending order, so the smallest number to the largest number, and anything that we have multiples of, we're going to use that exponent notation that we learned last chapter. So this is going to be 3 cubed times 5 times 7. Let's take a look here at 260. We'll start off with the 260. And it does end in a 0, so that means that it's a multiple of 10, but 10 is not a prime, so we want to be thinking of prime numbers here. So 5 will go in, and 5 is prime, so when we put 5 in here, we're left with 52. And now 52 is even because it ends in a 2. It means it's divisible by 2. So we're going to divide by that 2. And this leaves us 26. And again, 26 is even. So it is also divisible by 2. And that leaves us with a 13. So when we get the prime factorization of 260, it's equal to 2 squared times 5 times 13. Okay. There's another method that can be used here, and it is called the alternative scaffold, and it's really more like a table, but let's look at it here. So what we're going to do is we're going to kind of set up like a T-chart from algebra, feels like. We're going to put the number 144 here, and then we're going to divide, and we're going to say what can go into 144, and 2 can go into 144, and that leaves 72. And what can go into 72? 2 goes into 72, and that leaves 36. What can go into 36? 2 can also go into 36, leaving 18. 2 can also go into 18, leaving 9. Now 3 can go into 9, leaving 3, and then 3 goes into 3, leaving 1. Now the thing you have to keep in mind with the scaffold is you always, the last number on the right must be a 1. And we get our factors from here. We could also call them divisors, remember. So 144 in prime factorization is equal to 1, 2, 3, 4, 2 to the 4th power times 3 squared. Let's do one more. Let's go with our 336. And here I'm going to put I wrote 2 down there, but I think I'll just follow what I did in my notes just so the math will go easier. I did 3. 3 goes into 336 112 times. Now 2, 3, 4, if we add up the digits to 112, 3 doesn't divide that again, but 4 divides it because the 4 divides 12, but again 4 is not a prime number, so we'll just hop on here with 2. 2 goes into 112 56 times. 2 will go into 56. 2 goes into 56. Look, I just changed my way here. 28 times. 2 goes into 28 14 times. 2 goes into 14 7 times. And 7 goes into 7 1 time. Okay, and so that tells us that 336 is equal to how many 2's do we have? That will be 2 to the 4th power times a 3 times a 7. And if you're not sure, you can always multiply this back out and check it. That's like the coolest thing. Probably the thing that I do most often, and definitely the thing that I teach my students in college that need you know, some help in factoring stuff, is a straight up factor tree. And a factor tree is good because you don't have to start with the smallest number. You can go with whatever you immediately see here. So of course, 145 doesn't have a whole lot of options here. We're going to say 145 goes in 5, goes into 145. 5 times 29 is 145, and then we're going to check to see if 29 is prime, and it happens to be prime, and so we know here by our factor tree that 145 is equal to 5 times 29. Remember, to be in prime factorization, it has to be prime numbers. So if it's a number that is not prime, you must break it down to its prime pieces. Let's look at our 945 here. When we take a look at this guy, nothing jumps out really straight at me, so I'm going to go ahead and divide it by 5, and when I divide by 5, I get 5 and 189. As I keep on going, 189 is 3 and 63. 63 breaks down as 3 and 21. And 21 breaks down as 3 times 7. Now, this is what I always tell my students. Anything hanging off the end of the branch being these little lines that are sticking down, is one of the prime factors. So I have 5, I have 3 3's, and I have a 7. So 945 is equal to 3 cubed times 5 times 7. All right, so Knowing how many divisors a number has is a big important thing, and so the number of whole number divisors, we're going to be given a theorem here. It says if D is a divisor of n, where n is not equal to 0, then n divided by D is also a divisor of n, and that makes sense. Remember, for D to be a divisor of n, D divides n, that means that for some other number, we'll call it, for some sort of number P, maybe I don't want to talk about it like this, but anyway, I'm going to keep on going here for a second. D divides n is equivalent to us saying n is equal to some number like k times D, where k is just a whole number, a unique whole number. Okay, remember that. We've done that. So it makes sense that we can divide not only out the D here, but we could also divide out the k. So all of these become divisors as well. The second theorem's a little bit more useful as far as something that we're going to use here. It says if P and Q are different prime numbers and M and N are unique whole numbers, then when we have P to the M times Q to the N, that has M plus 1 times N plus 1 total divisors. So here's an example. Let's just say, let's see how many divisors this number is, and I don't know what this number is because I'm just going to make some crap up. So I'm going to go 2 to the 4th times 3 times 5 to the 7th. Okay, so if this is our number, this is equal to our mystery number. We don't even know what, we don't even care what the number is, our mystery number. Let's find the divisors. The total divisors are equal to, and what this theorem says is basically we're taking the exponents and adding 1. Okay, so it was going to be, we're going to have 4 plus 1 times, remember this 3, if it doesn't have anything there, it's an implied 1, so our next one's going to be 1 plus 1. And then finally we have our 7, so it's going to be then times 7 plus 1. So our total number of divisors here are going to be 5 times 2 times 8, which is 80. Okay, so with that being explained, find the total number of divisors of the following whole numbers. And notice I wrote here that they must be in prime factored form to implement the theorem. So the first thing we need to do is put this in prime factored form. Now, this is equal to 10 to the power of the number of zeros that are here. So 10 to the power of 6. So if we take 10 to the power of 6, that is not prime number, so we're going to have to break that 10 into its prime factorization. Now, I believe we learned in Chapter 3, I'm pretty sure, unless it was in 4.1, but I feel like it was in Chapter 3, that there is the exponent power, that when we have two things multiplied together raised to a power, we can raise each of those things individually to that power. So this is equal to 2 to the 6th times 5 to the 6th. So the number of divisors is equal to 6 plus 1 times 6 plus 1. The first 6 coming from here and the second 6 coming from there. And so that is 7 times 7, which is 49. So there's 49 total divisors. We're going to look at it the same way here. Now, how can we break down 210? Well, I'm going to go for 21 times 10. That's going to be raised to the 10th power, and then I'm just going to keep on breaking that up. So 21 is 3 times 7, and 10 is 2 times 5. All those are raised to the 10th power. I'm going to put them in order because that's what I do. I like to stay consistent with that, and it is important to kind of stay consistent with students. Sometimes the littlest thing that might have nothing to do with what you're actually talking about could throw them off. So try to stay consistent. It's not perfect, and I can't always stay consistent, but it is definitely helpful if you can. And here our number of divisors in this case are going to be 10 plus 1 times another 10 plus 1 times another 10 plus 1 times another 10 plus 1. And that is going to be 11 to the 4th power, which is 14,641. So that's how many total divisors 210 to the 10th power is. However, 210 to the 10th power is a really, really big number. Okay. All right. So because every composite number is comprised of the product of its prime number divisors, and every composite number has only one, a unique string of prime numbers whose product equals that composite number. To determine if a number is a prime, you must check all the prime numbers less than that number under investigation. Sometimes that could be a big list. Let's just take a look at what we've got here. So, is 91 composite or prime? Well, let's see. Let's just start listing some prime numbers here. So we got 2, 3, 5, 7. It's not that they're odd because 9 is not prime, but the next prime number is 11, then 13, 15 is a no-go, 17 is prime, 19 is prime. What's the next one? 23. Think about it for a minute. I'm giving you a second. 29, 31, 37, 41, 43. Anyway, we got some going there. Okay? So, basically, we need to know is 91 composite or prime. And so I'm just going to start low. I'm going to check 2. Does 2 divide 91? Nope. Right? 91 is not even. 3 divide 91? No. 9 plus 1 is equal to 10. Not a number that's divisible. 4, no, because 2 was not good. 4 is not even a prime. Let's try 5. We know 5. Nope. Last digit is not 0 or 5. Okay. 7. Well, I don't know about that. We might actually have to try 7 out over here. That's not one that's got any clear rules to it. And let's go 7 into 91. 7 goes into 91 once. Bring down the 7. 21. Oh, yay! So this is yes. 7 divides 91, so 91 is composite. Once you find one, that's it. There's no need to go any further. But you could see, what if this was the number 9,991? This could be pretty tedious, and so that brought us to this next theorem. If n is a whole number that's composite, that means that it is made up of more than one prime number multiplied together, then n has at least one prime factor, p, such that p squared is less than or equal to the original number. And that brings us to a second theorem, and the second theorem says if n is a whole number greater than 1 and n is not divisible by any prime number such that p squared is less than or equal to n, then n is a prime number. In other words, if you check all of the possible primes that fit the criteria of p squared is less than or equal to n, and you find none of those numbers work, there's no reason to try any other numbers, it means that you have completed the list. Now, this is a super duper powerful theorem. The p squared less than or equal to n means that at least one of the factors must be less than or equal to the square of the divisible prime. And this theorem doesn't directly give you the actual prime factor that you're looking for, but it provides you with a tool to manage the list of all the possible prime factors. And frankly and honestly, in practice, certainly through my career in mathematics, if I'm looking for prime factors of a number that is large, the first thing I do is take the square root of that number, and that tells me the highest prime that I'm going to have to go up to. Nobody wants to be doing scratch long division on the side on a piece of paper well beyond the numbers that you need to be checking. So this theorem just really gives you a point of which you can decide you have checked all that you need to check. All right, so we continue on with these theorems, putting them all together here. If p and q are unique prime numbers and n and m are whole numbers, then p to the n times q to the m have n plus 1 times m plus 1 whole number divisors. We just saw that. In general, as long as it's a bunch of different primes, and it could be a whole bunch of different powers, the number of divisors is whatever that power is plus 1, all multiplied together. And then I wanted to put a note out there, at least make you think about this, and you probably already know this, but you haven't really thought about this, but this is always great to keep in mind. Any two odd numbers that are multiplied together will give you an odd product, and any product that is multiplied by an even number anywhere in it is going to give you an even product. Okay, so let's look here and let's determine the number of factors or divisors of these numbers. So this first one here, 1360, first thing we have to do, remember step 1, find the prime factorization. Okay, so I'm going to do that first, 1360, and I'm going to just make myself a nice pretty little table here. I got 100 times 136, and that won't be 100 because that would be the wrong thing. That should be 10, my bad, sorry y'all. Let me fix that. Oh, you know what just happened? I just skipped ahead. No, it won't let me go backwards. Okay. I'm going to post on D2L because I do not want to do this over again just because my hand slid across the screen. I will post on D2L a just the two problems that I didn't get to show you worked out so you can look at them. Okay, but that brings us here to perfect squares. And what is a perfect square? A perfect square is a whole number that is the perfect square of another whole number. In fact, every whole number has perfect square associated. And the first 15 perfect squares are this: 1, 4, 9, 16, 25, 36. And you can see the list. How do we get the perfect squares? Well, the first one is 1 squared, second one is 2 squared, and so forth. Now I'm all scared to even use my pen here. Let's see, this is 1 squared and 2 squared, dot, dot, dot. This guy right here happens to be 15 squared. So these are the natural numbers in order multiplied by itself. These are called the perfect squares. Okay, and that gives us a theorem. And theorem says a whole number is a perfect square if and only if it has an odd number of factors. Now, the power of the if and only if statement is that it's contrapositive, and we studied this a little bit in our first unit when we did some logic there. In contrapositive statement, the contrapositive of a statement given is also true. So the contrapositive of a whole number is a perfect square if and only if it has an odd number of factors would be, if a number does not have an odd number of factors, then the number is not a perfect square. I'm sorry that my picture has to eclipse that. That really sucks. I'm trying to get better about that, but anyway. Okay. So that's the idea about the perfect square, and the reason I bring it up here is I'm going to show you another proof. Show that a whole number is a perfect square if and only if it has an odd number of factors. So here's the proof of that. I did the proof kind of in blue here, and so let's see. Let m be a whole number. Let m be a whole number which makes m square a perfect square. If the prime factorization of m is p sub 1 to the n sub 1 times p sub 2 to the m sub 2, what this actually means here, all these p sub 1s and n sub 1s and 2s and k's and all that, is these could be completely unique primes like 2, 3, 5, 7, 17, 31, 47. It could be any prime, and the n's being n1, n2, blah, blah, blah to nk could be any numbers. It could be any whole numbers, and that we write it like this so that everyone can understand that you mean that they could be anything. Okay? So once we have described what n would be, m would be, which was a prime raised to a power times another prime raised to a power to however many times. Then we know that m squared would be that prime raised to 2 times that power times prime 2 raised to 2 times that other power, and so forth. And that just is from the law of exponents. And then we know from the previous theorem that we just had that the number of divisors of m squared would be 2n sub 1 plus 1 plus 2n sub 2. In other words, all of those exponents added together. And the fact that an even number plus 1 is always going to be odd, and all odd numbers multiplied together are going to produce another odd. We note that all these factors here are odd. And when you multiply odd numbers together, you get an odd. Therefore, a whole number is a perfect square if and only if it has odd factors. And just consequently, there are tons and tons of special primes. There's twin primes. There's Pythagorean prime triplets where they come in threes. There's the Mersenne primes. There's more primes than I could probably list. If you go and take a look at Wikipedia under prime numbers, they've got a nice list of all the special primes, And I always have students wonder why prime numbers are so important, but prime numbers are the foundation of internet security. It's a field of mathematics called cryptography, and that is how we keep everything safe. And I know that sounds absolutely insano, but I challenge you to look into a little bit of cryptography and see what it's all about, and the fact that the internet is literally dependent on people that cannot factor big, huge prime numbers. Anyway, okay, I digressed. I was trying not to digress in any way. I'm trying to keep these as short as possible, even though I have a lot of content to cover. Finally, I'm going to end with a question here. It's like a homework question, and I wanted to kind of give you an idea and a strategy on how to solve something like this. So it says a farmer has fewer than 50 potatoes, and it just say he's got them in a big barrel, and he can't count while he sorts. I don't know, but anyway, just pretend. Remember, mathematic word problems are usually the most obscure. Anyway, so he can put them in piles of 2, he can put them in piles of 3, 4, 6, or 8, but every time he piles them up like that, he always has 1 potato left over. So I want to know how many potatoes he has, and you might think, how can I figure out how many potatoes he has? But we can use number theory here and divisibility to figure this out. So basically what we're given here is a list of bad divisors. The bad divisors. So we need to check out the bad divisors. I'm just going to list them. There was 2, there was 3, there was 4, which we know is can be written as 2 squared. There was 6, that one's bad, and that could be written as 2 times 3. And then there was 8, and that is written as 2 cubed. So we've already been told that these are bad, but a good strategy is to just add 1 to each of these things and see what happens, right? So I'm just going to add 1. Plus 1, that gives me 3. Well, this was bad to begin with. Bad from original list, right? And if we add 1 to 3, well, that's 4. That is also bad from the original list. But if we add 1 to 4, we get 5. So let's check that out. So 5 squared is equal to 25. And if we had to do them in 5s, we'd have to have 5 groups of 5, which means it would force us to have 25. So let me put it this way. So if 5 was a divisor, we would have to have or we could have 5 groups of 5, right? We couldn't have 2 groups of 5 because 2 is not a divisor. We couldn't have 3 groups of 5 because 3 is not a divisor. So we could have 5 groups of 5. Okay, well, let's just keep on going here. How about if we add 1 to 6? Add 1 to 6, that gives us 7. Let's see about 7. Well, if we did the 7 squared would give us 49, because if 7, not 5. So for the same logic though, if 7 is a divisor and we would have to have 7 groups of 7, we would have to make, in this case, 7 groups of 7. Okay. And I'm committed here. Let's check the other. Add 1 here, and that's going to 8 plus 1 is 9. But we're not well, I'll just do it here. Let's consider 9. I'm going to say 9's already out because 3's not a divisor, but sometimes 9 can be a divisor where 3 is not. So maybe, I don't know. So let's see, what would 9 be? That would 9 squared would be 81, because if 9 is a divisor, we would have 9 groups of 9. Okay, so we've run down all the possibilities here, and then we're going to come back up here to our question, and we see in our question that the farmer has, where's my pen? The farmer has fewer than 50 potatoes, so this one's not going to work. And 25 is actually not the solution. Because there is one close there. There is one that's closer to 50. So farmer has 49 potatoes. And so he winds up with 7 piles of 7. Although it didn't ask about that, but we needed to know that to work it out. All right, well, I appreciate you guys. And I will get the GCF LCM up ASAP.